what we've been talking about, by the way, hi Olivia. I hope that this works. I know we're in the dark and looking at this screen, but at least you get to get some idea of what we're doing here. We're talking about experimental design, the scientific method, and I want to use this example because I think it's a really good one of how you go from making observations to making a hypothesis to designing an experiment, interpreting the results, drawing conclusions. And so we're going to use the example of Dr. Betsy Manning. She's a field biologist. She's collecting data. By the way, field means somebody who is out in the world, not in a laboratory. She's a field biologist. She's collecting data on the different heights of mountain star, a small annual plant that grows in patches along the mountains shown below. And does anybody know what an annual plant is as opposed to a perennial? No. It's a plant that grows from seed every year, whereas a perennial is something like a shrub. The shrub stays there year after year and keeps getting bigger. An annual is like a petunia or something like that. Like a perennial is like a rose bush that re-sprouts every year. But an annual starts from the ground, grows from a sprout, makes seeds, dies in the winter every year. Anyway, help Dr. Manning collect data on two populations of mountain star found growing at two different sites, one at 1,000 meters above sea level, one at 2,000 meters above sea level. You can access this activity by yourselves, by the way. When I give you your book, I'm also going to give you sign-in information for how to access this. But anyway, so okay, I'm going to click next. So we're looking at things that are going 1,000 meters up. It's about 3,000 feet. 2,000 meters up, that's about 6,000 feet, so twice as high. All right, so we're going to measure the plants. We're going to measure the plants by clicking on this, and then we're going to click on that later and measure those plants. All right, and so I'll get down here. The way that we do this is we run the slider up and down, and that tells us about, you can see here where it tells us the height of these plants in centimeters. Why centimeters? Because we're scientists, that's why we use the metric system. Anyway, plant 5 looks like it's about 36 centimeters. Plant 6 looks like it's about, 43. And then plant 7 looks like it's about 42. So what was that? 36, 43, 42. And we'll do the next set, also from 1,000 meters. Looks like we've got 38, 41, 40. 38, 41, 40. Okay, so who wants to do a little calculator work for me?
Me.
Okay, you get the big calculator.
Yeah.
So you can see the numbers in the column there?
Yeah.
Will you add the total, add them up for a total?
I can't really, but y'all anymore.
Well, right. Right. Oh, hold on, wait, no, before that, I'm sorry. In a second you're going to do that. It wants us to enter the 2,000 meter plants first. Then we'll give somebody else a calculator and they can do the totals of those. Okay, if you want to, you can do those totals while I'm putting these others in. Okay, so the ones at 2,000 meters, what do we notice right away? Are we on our phone for a school-related reason?
Yeah, I'm actually getting to a calculator and I was going to tell you what it was.
Oh, alright. Well, you can do, how about this? You do the second column.
Calculator.
Got it.
Wait. Is it all of those plants?
Well, with the first set that we just did, all of these are from here. Now, these plants are from here, from 2,000 meters.
So I have to do from plant 1 to plant 10?
Right, you're doing plant 1 to plant 10 from 1,000 meters. Mr. Romo do plant 1 to plant 10 from 2,000 meters.
39.
So you want me to add all those?
39.
Well, you're going to add the second column that I haven't filled in all the way yet. Okay, so the first one I'm thinking looks like about, I'm going to call it 12.
Plus.
The second plant, the plant 6, we'll say, I'm going to call that one 9.
40?
This one, we'll call that 12 also. And we'll do the next set. I'm thinking 13, 11, and I'm just going to say also 11. Okay, so calculate. All right, and so yeah, for your column, for the 1,000-meter column, Cassie, what do you get for your total?
What?
For this column here, 1,000-meter, what do you get for your total?
398.
398.
I should be right.
Okay. It could be. I might have entered them a little bit wrong too, so don't worry about it. And so,
Added all of them.
what did you get for column 2?
Added all of them.
1 minute. We're talking centimeters, not minutes. Just kidding. Bad joke.
So that was.
Do I add up the 2,000 meter too?
No, that's right.
Wait, was I supposed to put in the 2,000 meter, like adding the 2,000 meter also?
That's the only one you're adding. So no, I just want you to add this column of numbers.
I only got 100.
You got 100? Okay. 100. And so if we did now we're going to do the mean height, because the reason, how come we measure more than one from each place? By the way, how come we don't just take one from each place?
Because you want to average them all together.
You want to get an average because that's going to give us a better idea, right? It's like if I was to say, how tall are human beings anyway? And I just picked one of you, that wouldn't really give me a great idea of how tall human beings are unless the one happened to be exactly the average of the whole class. So, all right, so the average or mean height at 1,000, what are we going to do? How would we get that? All right, we'll take our 398 and divide it by 10. I'm just going to write, what would that be? 398 divided by 10.
When you divide by 20, since it is 20.
No, because we're just, so the average, remember, don't forget, we're trying to compare these two.
Oh,
And so we'll do the average of these.
I thought you were doing the average of like all of them.
Of all of them? No. 39.8. Right, folks, a little math trick. Anytime you want to divide by 10, you can just take the decimal and move it over 1. And so what does that mean the average of the second column is going to be? 10. Very good. All right, and so let's check our answer. Okay, they say this was 400, but that means, but let's see. Oh yeah, I measured this one at 36. They say it's 37, and I don't know where the other difference is, but anyway. They say that, so what they say is that these average about 40, these average about 10, so 4 times taller. Let's look at a graph to help us see the difference.
There's more water.
Well, okay, that's what we're going to talk about. That's the next thing we talk about. So, 4 times taller on average. Okay, and so this is asking for 2 observations. Now, observations aren't conclusions. Observations aren't explanations. So just don't overthink it. What's an observation we can make about this data?
The plants grow taller at a lower altitude.
Yep. Okay. Now, they ask us for 2. As far as I'm concerned, that's it. I mean, you could say the other is that there's a difference. Do you have another?
No, I'm agreeing with
That's all I see. I think they're overthinking it. Whatever else they want, we're just going to move on. So now they want us to make an inference based on these observations. Inference. What is an inference? It means to. An inference is when you infer something. Like a conference is when you confer, people talk together. A reference is when you refer. But what's an inference? What does it mean to infer something?
To tell?
To tell, you mean,
To let someone
no, that's different. To infer, like if I see something out in the world and I infer something from it,
Learn.
that means to draw a conclusion or to make a connection. So I see that there's a difference in the heights, and I might infer a number of things. Well, so in other words, to draw a conclusion based that you think might lead to a hypothesis. So there seems to be some sort of difference. Altitude seems to cause a difference between plant height. How about that?
So is it a possible conclusion?
Yeah, right.
Possible conclusion.
Altitude seems to affect plant height. Infer. Let me just see, make sure this isn't my wife, because I always want
I like that ringtone.
Oh, crud.
What?
What?
I missed a meeting.
Oh shoot. Sure, why isn't
It's the registrar. He's calling to tell me I missed a meeting an hour ago.
What's the registrar?
Mr. Stacy,
11:20.
11:20. That's right. Stop ringing, I know. All right. So, all right, just curious. Let's talk.
Jim.
Answer it and then hang up.
Yeah, he'll love that. Like he's not mad at me
It's
already.
right. It's right on the board.
Is the person?
I know. That's why I wrote it up there.
Is the person in the school?
Yes. Okay, never mind about that, folks. We're here to talk about this. So let's what do you think might be causing this? Just curious. How about some hypotheses about why? We don't really it doesn't really get into this ultimately, which surprised me. But why do you think plants at a higher altitude might be shorter?
Less oxygen.
Less oxygen. Well, actually,
Less carbon dioxide.
less carbon dioxide. Less stuff. They actually take in carbon dioxide and put out oxygen. But you're right. Less thinner atmosphere. All right. Any other ideas?
Cold.
Different temperature. Yeah, it's colder up high. Okay. That's two.
Different soil.
Different soil. Yeah, soil might be rockier up high. That's an email from Mr. Stacy.
Yelling. Yelling at me.
Be like,
Right.
I got sick.
He's just gonna come up and
You're up
Right.
everywhere.
He is. He's going to come up and pound me right in front of all you guys.
it'd be awesome.
And I have one too, which is that if you've ever been, you know, like for example, if you go to Mount Mansfield, which is way up near Stowe, it's the only one of the rare alpine ecosystems in the States, let alone Vermont. But it's this sort of special line you cross where it's colder, it's constantly windy, and it really just never warms up quite as much. And you have plants that grow there that don't grow anywhere else, but also you'll see the same versions of plants, like there's one called Devil's Paintbrush, hawthorn maybe, it's Australian. And down here, when you see it in fields here, it's got these beautiful red flowers. It grows about this tall.
Yeah, I see
But
that.
when you see it up on Mount Mansfield, it's about that tall. And one of the reasons I feel like is because there's this constant ripping wind that goes through all the time. And so the smaller you are, the less of your heat you're going to lose to the wind, and also the less you're going to get smashed around by the wind. So I'd say wind is another one. But anyway, let's look at Dr. Manning's notebook and see what Dr. Manning said about this. Dr. Manning makes an observation, and I know this is hard to read on the video, so I'm just going to say what it says. There is a mean height difference. That's her observation. We saw that too. And her inference is the growth rate of plants might be related to altitude. Yeah, well, you know, guess what, folks? She's got a PhD, and you guys came to the same conclusion. Nice work. Okay, and so moving on to the second part of this activity, let's form a hypothesis. So we use our observations and previous experience and knowledge to come up with a hypothesis. And so Dr. Manning's notebook says, Wednesday. Calculated the mean height of mountain star plants at various altitudes. These plants seem to be separated populations of the same species The mean plant height goes down as the altitude goes up. What might cause this variation? Nice notebook.
Water.
Good thought. And so let's have a hypothesis. You think it's water? So okay, water, wind, altitude, temperature, and soil. What category, broad category, could we put all of those into?
Environment.
Environment, right? Environmental effect, right? An effect of something in the environment. Environmental effect causes the difference. What's the other possibility? I'm not expecting you to necessarily get this, but what would be the sort of opposite of if it was caused by the environment? What's the other thing it could be caused by? I'm not sure. Wait,
Agriculture.
agriculture. I'm not sure about that. What did you say? Chemicals. Again, those would still be environmental things. What is something? So, in other words, when I say environmental, it means something the plant is experiencing in the outside world is causing this difference. Is there another explanation? What's that? Bugs. Well, that's another environmental effect.
Bugs.
Tell you what.
Elements.
What's that?
Elements.
Elements? No, again, same thing. Let's look at Dr. Manning's hypothesis, because this wasn't... Well, anyway, let's look at Dr. Manning's hypothesis. Dr. Manning made two alternative hypotheses. One, this is the one that we didn't think of. When I say we, I mean you, but that's okay. I didn't think of this the first time around either. Bing. Stay connected so we can hear more from Mr. Steve. One, the height difference between plant populations is due to heredity.
What's heredity?
What is heredity? Somebody just said it. Genetic difference,
DNA.
genes, DNA. You're born with it. In other words, I have, or my poor son has two short parents. I mean, at least I assume that. I assume I'm one of them, you know. But anyway, the point is, I'm 5'8". My wife is 5'2". Unless, it's very likely because of heredity that my son is going to be somewhere in between those, or maybe he'll just be my height. Really tall people, really tall children. So that's heredity. What you're born with, your DNA, your genes. So that is stuff that's not affected by the environment. The other hypothesis she makes, the height difference is related to the two environments, 1,000 meters and 2,000 meters. All right, so now they say, write your ideas for an experiment to test these two hypotheses. How might we go about testing these two hypotheses? Let's think about that. All right.
Grow them in different environments.
Grow them in different environments. Genius. Yes. And it turns out, different environments. What do you mean by different environments, though? Like completely different environments? Take them to New York City and grow them in a gutter? Grow them between cracks in the sidewalk? Or what were you thinking when you said that? What did you mean?
Like since one grew at 1,000 meters above sea level and the other one grew 2,000. Like something like that, but not this.
Okay.
If that makes sense.
Can anybody jump onto that? Because yes, but let's be a little more specific. Anybody want to jump onto that besides Miss Elliott, who's raring to go here? I can see she's jumping up and down in her seat.
Did you get your rat?
Did anybody have an idea? So growing them in different environments is sort of the cue. Let's say they make seeds. Yeah, what do you say?
What if you scoop one up from the 2,000, put it in the 1,000, 1,000 to 2,000?
That's I think you're both. Is that sort of like what Victoria just said? Is to scoop them up from the 1,000 and put them at the 2,000, or vice versa. And it turns out that's exactly what she does. We can design an experiment to test both hypotheses by growing seeds collected from the two populations, 1,000 meter and 2,000 meter, in a test garden located at 1,000 meters, right? And so, with the same soil, light, and weather. In other words, they'll be in the same environment. They'll have all the same environmental factors, and that way, if they grow the same, we'll know that the difference was due to which? Environment or heredity? That's right. Well, because if we put them in the same place and they grow the same, that'll mean that the difference was because of their two environments. If we put them in the same place and they grow different, that'll probably mean it's due to heredity. Okay. Oh,
I'm
thank you.
having too much fun with this.
Okay, thank you. So all right, so let's do this thing. All right, so we're going to click on the seeds. These are the 1,000-meter seeds. By the way, whoops. Hey, here's a vocabulary word. To test the hypothesis, Dr. Manning collected mountain star seeds. We've got about 5 minutes left here, folks, so stay with me. Can you wait just a few minutes? Thank you very much. To test the hypothesis, Dr. Manning collected mountain star seeds from the 1,000-meter and 2,000-meter sites. Click on the seeds at 1,000 meters to plant them in a test garden located at 1,000 meters above sea level. These are your control group. The control group is the group that you don't change anything with, right? We take the seeds from the 1,000 meters and we grow them at 1,000 meters. That's exactly the way they were before. So in other words, if we took them both to 5,000 meters, then we'd be changing too much. If we took them both to 1,500 meters, we'd be changing too much. With an experiment, you always want to keep one group that's the same. That's your control group. And so we're going to plant these seeds from the 1,000-meter plants at 1,000 meters. And now the next group, these are going to be our seeds from 2,000 meters, and we're planting them at 1,000 meters, just like the other ones. That's your experimental group. That's the ones you're really changing a variable with. And again, you just want to change one variable. We're not going to also plant these at 1,000 meters and then water one more than the other, or put salt on one and no salt on the other. Like you only want to change one thing. Otherwise, it's too much. By the way, is the screen still going here for that? Or did it turn
Yeah.
off? Oh, good. Great. So I'm going to click on the seeds and we're going to plant them. And now we're going to click on 1 year later. Now it looks like they're the same, but in order to see for sure, we have to measure, because I think once we measure, you'll find out that this is a deceptive picture. But anyway, so let's measure. Click on the 1,000-meter plants to begin measuring those. Okay, so looks like we've got. Try to hurry here because we're running low on time. We've got 29, 33, and 30.
29, 33, and 30.
29, thank you. 33, 30. And we'll do the next set. I'm seeing 32, 31, and 31. 3, 2. Oh, that's just a 3, 2, 3, 1, 3, 1. Okay. Now we'll click on this garden. Right? See, the picture was deceptive, wasn't it?
Oh my god.
So I'm seeing 15, 15, and 13. 15, 15, 13. Next set. Don't worry, folks, we're almost there. You guys are doing a great job, by the way. 17, 16. No, don't start shuffling around and getting ready yet. We're 6, 7 minutes from that yet. So you made me lose track. 17, 16, 14. 17, 16, 14. Thank you. Okay, now calculate. Who wants to calculate?
Oh, what should I
Zach. Get that. Anybody else want to calculate here?
186 and 185.
Whoa! Wait, what, you did both of them?
Yeah.
Okay, I'll tell you what. Let's have Zach do these. Just double check, and then what did you get for the 2,000-meter ones?
I think they were 100.
100. Okay, so we have 100 over here. I'm not sure I agree with your measurements on the first one. 60.
Oh no, I'm wrong. 130. 130.
85,
I got 309.
309, that's what I got too. I'm so sorry.
That's alright.
Okay, and so let's say the average for these is 30.9. The average for these is 10. Can we all agree on that? All right. Wait. Oh, wait. What happened?
I'm checking the.
No, each one is at least 10, and some of them higher than 100.
Oh, you're right. Yeah. You're right. 150. Okay. So, all right. Looks like we have an average of 15. I apologize. All right. So let's look at the graph. So it still looks like we have a clear difference. The 1,000-meter ones are 3 times taller than the 2,000-meter ones. You guys still with me in the back there?
Oh, I'm
Good.
not back.
You're not a guy and you're not in the back. But that's okay. I'm glad you're still with me too. All right, so conclusion. What do we say? What can we conclude then? Heredity. I think we can conclude heredity here because no matter where you put them, there's still a height difference. So if it was environment, they would have grown the same in the same environment. But it appears that we've got some heredity going on here. Heredity. Dr. Manning's conclusion? Now we know that something other than environmental factors is at work here. Our experimental results support the hypothesis. The difference between two populations is due mainly to heredity. Okay. And that's it. So that was nice, folks. Let me I'm going to turn this off. I'm going to turn the light on. We're going to have to continue.
Are you gonna collect your homework?
We're going to have to continue this discussion tomorrow because there's a few vocabulary words I have to give you. Olivia, thank you for your attention. We hope you enjoyed our show today. We hope you can see any of it. You better watch it. The magic number is 3. I will ask you later what the magic number is, and so we'll see if you watch it. Nobody tell her the magic number. Right? It's like Pee-wee's Playhouse. Remember the magic word on Pee-wee's Playhouse? Anybody ever watch that?
Do you want this homework?
Oh, sign it.
No.
Thank you.